this A-vector emission, how does it affect the intensity and things like this. Okay? And usually you come in, interact with your sample, and the photoelectron come out, and you have a device called electron spectrometer that you can move around in any space to detect this photoelectron and to analyze how fast this photoelectron are moving in order to relate to this photon absorption. Okay, so that is a very complicated, somewhat complicated topic, which I won't talk about until later when we talk more about photoelectron spectroscopy. But for now, I just want people to have a taste of what we expect to see later on, like this. Okay, so let me go back to continue with this. So people can go to the link and take a look at that lecture notes on this. So here we talk about this, and then of course you can have what you got here. Right, so this is a basic principle of electron emission. Photon can come in, can excite, can remove the electron from your valence shell, or you can move the electron from deep core level like this. If you remove the electron from the valence shell, you got the electronic structure like this, called a band structure. We'll come back to this. We have to explain what is momentum direction, all this symbol, we have to explain that a little bit. It's related to solid state physics, but it's quite simple to think about once we understand the physical structure of the material. And then you can, of course, look at the other topic that we were planning to examine here in this course is the composition. So we have, these for electron spectroscopy give us the electronic structure, both material, nanoparticle, nanoscale material, not just surfaces, but composition, you can do secondary ion mass spectrometry, and you can look at the elemental. This is more of an elemental technique. It's sort of like sandblasting a material and look at the emitted material by mass spectrometry, and then see what you get, because it's like etching, and then look at the etched material and try to infer what is the original layer that you've got. Okay, so we have in MAUDLAB we do have a SIM spectrometer, but we will have a state-of-the-art coming in a year, and people interested in come and see this. We have one of the best to look at biomaterial spectrometer coming. And usually what you see, you have some machine, and you, for now, think of some machine. What you're looking at is essentially very much like mass spectrometer. You have a mass spectrometer of the material that you sputter off, and you analyze the sputter off material, and from this mass spectrometer, you can build up a map of what you've got. So here is a map as a function of depth. So as you etch more and more into material, you can look at the elemental composition as you go through. And oftentimes, what is interesting about this is that oftentimes the electronic engineer are very interested in this. The reason is that they want to know how to dope a certain material, so they can dope a material by implanting, let's say, boron into a silicon, and we want to know the dopant level. So they want to, how deep is the dopant? So they can calculate it by etching, essentially ion etching, which is the SIMS technique. You can get this information as a function of depth. If you remember the Evans plot, SIMS is extremely sensitive quantitative technique if you know the sputtering rate. And because you're using advanced mass spectrometry, and mass spectrometry is extremely sensitive. You can build up mapping and stuff like this. So here, finally, you can also use OJ, not just mass spectrometry, you can use OJ electron spectroscopy. OJ electron, what is OJ electron? We talked a little bit about this from time to time. Let me just give you a quick explanation. OJ electron occur like this. So you can have incident electron as in the electron microscope, or you can have an X-ray coming in, and you excite. If you have high enough energy, it will remove electron. You will eject the electron. That is, of course, photoelectron, right, or backscatter electron that you see, right? So that's in my initial state. So what happened? You create a little hole in this intermediate energy level, and so so how do you fill this hole? Well, what you can do is that so here I have created a little hole. Let me just draw an empty circle like this to indicate the hole was created. So one way to fill this hole is that you have an upper electron come down to fill this hole and emit a photon, because there is spare energy when you come down to fill this hole. And that is called X-ray fluorescence or X-ray emission. That is EDAX that you see. Another way is that the electron can come and fill this hole. Instead of emitting a photon, right, a photon emission, you can emit an electron. This electron that kick out because this filled this hole and kick out, and this electron carry all the excess energy that you got. Okay, so instead of emitting a photon, you use an electron on the upper state and carry all the excess energy that you got. And this electron is known as OJ electron, and it's radiation-less decay because you don't emit a photon anymore. You don't emit like you emit a electron. And so this OJ electron comes out. And because the OJ electron involve energy level, you see this OJ emission involve energy level, it is material sensitive. So copper will have a different OJ line compared to gold. And so you can use, in fact, the kinetic energy of this OJ electron to determine what kind of material you have. So it's compositionally sensitive. So after emission, you would have something like this. Okay. So you can, in fact, build a OJ spectrometer, and WattLab has one that you can actually very surface sensitively to analyze the material you got. So here you have you can make a map. So you have oxide versus elemental. So I believe the yellow one is the oxide, and then the rest is elemental. You can essentially point by point analyze this OJ electron emission and build up the map. And remember, OJ emit the mid-free path of these fast energy are very slow, and they emit only in the top. They can come out only from the top 1 to 2 nanometers. So this is extremely surface sensitive for the material that you have. So OJ electron can be used for composition analysis of the element, primary element. This can be used to look at molecular fragments that you see. Yes?
It could emit a photon, but if it is emitting an Auger electron, then how is it controlled? Like, how do we make sure that it is emitting only as an Auger electron, not as a photon?
Okay, so the question is that how do we control whether the material is emitting photon or OJ electron? The answer is that you can't. They would emit both. They would have both OJ emission and X-ray emission. And the question is that what tool do you use to analyze? Do you want to analyze X-ray emission, or do you want to analyze OJ electron emission? Okay, so do not the atoms are not intelligent. So they don't decide what to emit. So when they absorb a photon, physics will occur, right? So emission of photon and emission of electron, photoelectron will occur. Okay, and of course we try to learn about what is the probability of this emission. So this is why people invented all this term, cross section. So electron emission, photoelectron emission, and X-ray emission have a cross section, and this cross section means that correspond to probability of emitting a photoelectron or probability of emitting a photon. So we characterize how strong an emission that will occur. They will occur.